Hi there, welcome back. We're starting chapter 1.1 in the Introduction to Statistics Think and Do book. And in this chapter we're going to introduce some terminology and some definitions, and a lot of people race through this part, and it's not, there's no formulas to really go through, but it's important. Words are important, and so it's worth knowing this information because we use this terminology throughout the book. It's also worth noting at this point that there's actually a fairly decent storm going on in the background, and I've stopped and started this video enough times that I'm just going to talk through it. So if you hear what sounds like thunder in the background, it actually is thunder. So we'll get started. And so as I start bringing up all these definitions and terminology, I want to go back to one statement that we mentioned in the introduction, and it's this one: the average pineapple plant is 3.47 feet tall. And I wasn't that pleased about this statement because it seemed too accurate, and I said, all right, I would find it a little more believable if they said the average pineapple plant is about 3.47 feet tall. Because they didn't measure every single pineapple plant. They took a sample, they took some, measured some, and got the average from that. But they're making this sort of sweeping statement about what appears to be all pineapple plants, and whether or not that's true, it's not clear. And so if they just put about in there, it would make it more believable. So that's what we did in the intro. So going back to our definitions and terminology here. So data is the collection of observations. This might be the heights of pineapple plants, or the favorite colors of 30 people in the classroom, right? So it's the collection of observations. The population is the complete collection of all members in a group. For example, for a pineapples problem, it would be all pineapple plants. So the population is every pineapple plant there ever has been. The sample is a subgroup of the population. Probably the sample in this case would be the group of pineapple plants used to arrive at our average there. And a parameter is a numerical description of some characteristic of the population, such as the average height of all pineapple plants. Right? We usually don't know. This thing is usually unknown, right? Because it's impossible, for our little example, to get the height of every single pineapple plant and get the average of all of those. So what we wind up having are statistics. A statistic is a numerical description of some characteristic of the sample. So we have statistic, sample, right? So that the example from the pineapple plant, that was most likely a statistic, but it was stated as if it might be a parameter. So one thing some students use to remember this: parameter starts with P, population starts with P, statistic starts with S, sample starts with S. And we will use these terms fairly regularly, so it's good to know what a parameter is, because usually we don't know what a parameter is and we have to estimate it with a statistic. Statistics, the practice, the art/science of statistics, comes in two forms. Descriptive, that's where you take data and you organize it and take averages or medians or quartiles and things like that. And inferential statistics is when you take sample data or sample statistics and make guesses about population parameters. So that's inferential statistics. That's sort of the guessing game. And the connection between these two is probability. All right. The first example, which is done here, I suppose I'm in charge of the lunches at Scooter's Super Summer Fun Camp. And you're looking to save some money by serving some cheaper macaroni and cheese. I currently serve the good kind. I'm going to serve the cheap kind, and I suspect that most kids won't be able to tell the difference. But before doing this, I actually take a sample of 40 kids, and of that sample, 26 could not tell the difference, right? So in my sample, certainly most kids could not tell the difference. And through the process described in Chapter 8, I will be able to conclude that most kids at camp, all the kids at camp, cannot tell the difference. Most of all the kids at camp cannot tell the difference. But that's based on a sample, so there's a chance I'm wrong. In this case, I have a 3% chance that I'm wrong. And I didn't make that up. That is calculated. It's not just me guessing. And that's, stuff we do in Chapter 8, so there's no reason for you to know immediately how that 3% came about, but we'll get there. So for this sort of example of inferential statistics, we start off the data, or the results from the 40 kids. The population I'm concerned with is all kids at the camp. The sample is the 40 kids that were in my sample. The parameter, what I would really like to know is what percentage of all kids. Right? Parameter has to deal with the population. The statistic is the 65%. That came from the 26 out of 40. So that's a statistic. It's a type of descriptive statistic. It tells me the percent of my sample. That could not tell the difference. And then the process of estimating the population, whenever I said most kids at camp, I'm estimating the population, is a type of inferential statistics. And the 3% that I'm wrong is a probability. So this is sort of all the different topic, the terminology we'll be throwing around and how it's used. So for your turn, suppose you have a sample of 230 college students. It's a sample. The average number of hours slept per night is 6.2 hours. After analyzing the data, I am 90% confident that the average number of hours of sleep for all college students is between 5.9 and 6.5. So I'm giving it a range here. Determine the following. What is the population I'm studying? I'm studying college students. The sample is the 230 college students that were in my sample. And the statistic is the average that I got from my sample, 6.2. And the parameter I'm seeking to find is the average for all college students, right? All college students. And I don't know exactly what that is, but I give an estimate on that parameter of 5.9 to 6.5 hours per night. What is the probability that my conclusion about the parameter is correct? 90%. That is a probability. And there's that probability, there's a little more subtlety to it than that, but that captures the idea. You're 90% confident, meaning you're pretty confident. Okay, so that's that. Your turn. Let's go on to some more stuff about types of data. There's qualitative and quantitative. Qualitative, also known as categorical, or basically descriptions, things that are non-numerical. Some qualitative data, such as ID numbers, student ID numbers, things like that, they look numerical, but they're really just names. It's a numerical name, so it's not really quantitative. Quantitative is numerical, right? Numerical counts or measurements or weights or heights, things like that. And they come in two different forms. Discrete means there's a little bit of space in between any two consecutive values, things like counts. Continuous data, there is no space in between possible measurements. And things like time, weight, height. And if you think about it, if you look at any two weights, is there a weight in between the two measurements? Is there a weight between 1 and 2 pounds? Yes. 1.5. Is there a weight between 1 and 1.5? Yes, 1.25. And can you continue to play this game indefinitely? You sure can. And that's what makes the data continuous. So continuous means the measurements are on a continuum. In between any two values is another value. Then we have levels of measurement, from lowest to highest here. Nominal, basically nominal comes from names. And they're basically categories, labels, names. Things they cannot be ordered, added, or averaged. All right? And usually this comes from qualitative data. Ordinal measurements mean you can order them, you can rank them, but the differences don't make very much sense. And it's sort of vague. Things like letter grades, you certainly know A is better than B, is better than C, is better than D, is better than F, but exactly how much better is a little ambiguous, right? Interval measurements, you can order them, and differences make sense. And this is sort of the oddball category. because it's almost the ideal situation, but not quite. And what makes a measurement interval and not ratio, because this is the best, this bottom one, is that ratios do not make sense. All right. And there's not many things in this category. There's two things in the interval measurement. There's dates and non-Kelvin temperatures. And here's what makes it special. If you look at temperature 10 degrees Celsius and 20 degrees Celsius, you know that 20 degrees Celsius is warmer, so you can order them. You know it's 10 degrees warmer, so you can get differences. But the ratio doesn't really make sense. 20 degrees Celsius is actually not twice as hot. The molecules are not moving. It takes a little bit of chemistry to understand what I'm talking about, but 20 degrees is actually not twice as hot as 10 degrees. And that's because 0 degrees Celsius is sort of arbitrary. It's not the actual lack of any heat. It's just the freezing point of water. So it's sort of an arbitrary 0. And that's what makes non-Kelvin temperatures less than ideal. Makes them interval measurements instead of ratio. Ratio measurements are the best. They can be ordered. Differences make sense, and ratios make sense. So this is the best kind of data. And so things like time, temperature in degrees Kelvin, which we hardly ever use, but that's just to distinguish between this group and the interval measurements. Counts, prices, things like that. Where ratios make sense. Length. Something can be twice as long as something else. Right? You can tell... you can take ratios and they make sense. And if there's a 0 length, that means that's 0, right? So it's not arbitrary. So the examples, the first group that are in the text, determine whether it is continuous or not continuous. Determine whether we're talking qualitative or quantitative. If quantitative, categorize as discrete or continuous. And then determine the level of measurement. And the level of measurement is one of these 4 right here. So if you look at the finishing times of the top 100 runners in the Boston Marathon, certainly quantitative because it's numerical. It's continuous because in between any 2 times is another time. And it's ratio because the ratios make sense and there's a meaningful 0. I mean, it's not that meaningful in the sense that if you ran a marathon in 0 time, you really didn't run it, but at least we know exactly what 0 is. And what I mean by ratios is if it takes one person 4 hours to run it, and another person 2 hours, a very fast person, then it took this person twice as long. All right, so the ratio makes sense. The ISBN numbers for all of your textbooks, they look numerical, and they are, but they are just acting as names. So it's actually qualitative data. And when you're dealing with qualitative data, the level of measurement is by default nominal. It's just names. Each of 12 hotels are ranked by the number of stars. This is quantitative because you're talking number of stars, right? It's discrete because you have 1 star, 2 star, 3 star. You don't get 1.5 star. Or maybe you do have 1.5 star, but do you have a star rating between 1 and 1.5? Maybe, and if you do you have it between that? Eventually you stop with this whole fractional star system. And so that's what makes it discrete. In between every 2 measurements, there's not necessarily another measurement. And it's ordinal because, 3 stars is certainly greater than 2 stars, right? We can all agree on that. But what is the difference? The difference is very vague. The difference is ambiguous, right? So it's not, we don't quite get to interval. Interval, we need differences to make sense. And ratios, if one hotel got 2 stars, and the other one got 1 star, is the first one twice as good as the second? I don't know. It's hard to tell. What does the difference even mean? So it's ordinal. You can rank them, but the differences are very ambiguous. So for the your turn, suppose I have 30 people in stats class. They must categorize themselves as conservative, moderate, or liberal. So they all write this down on a piece of paper, hand it to you. What you have, the data there is qualitative, right? It's just something that describes their political category. Now, if you were counting how many conservatives, how many moderates, how many liberals, then suddenly it wouldn't be qualitative, it would be quantitative. But since it is the actual names of their political affiliations, then it is qualitative, and by default, the level of measurement is nominal. Right? Let's see. B, the number of donuts made by baker on Sunday morning. That is quantitative. You're counting donuts. It is discrete. 1 donut, 2 donuts, 3 donuts. Right? There's not half donuts. There might be half donuts, but are there quarter donuts, 8th donuts, 10th donuts, 16th donuts, 100th donuts? No. So eventually it breaks down into discrete steps from one count of donuts to the next. So it's discrete data, and it's ratio. Right? The level of measurement is ratio in the sense that you can rank, if on one day he makes 100 donuts and on the next day he makes 50 donuts, or she. Certainly you can rank. There's more donuts made the first time. Certainly the difference makes sense. Made 50 more donuts. And ratios make sense. On the first day made twice as many donuts. Right? So that gives us the best situation. Count as a level of measurement ratio. The ratio level of measurement, which is the sort of the ideal numerical data type. Okay, the high temperatures for each day this week in degrees Celsius. This is our oddball category that I mentioned up here. Interval, but we'll figure that out in a second. It is the temperature, so it's quantitative. It will be a numerical value. It is continuous because in between any two temperatures is another temperature. Now your thermometer might not be that refined, but the lack of refinement in your measuring device does not change the level of measurement. So it's still a continuous level of measurement, or not level of measurement, but a continuous data type. The level of measurement is interval, right? Because as I mentioned in my last little demonstration up here, if it goes from 10 degrees in the morning to 20 degrees in the afternoon, certainly it got warmer, you can rank them. So you can order these two temperatures. Difference makes sense. But ratios don't make sense. It did not, when you do the ratio 20 over 10, you can put the degrees, it did not actually get twice as hot, right? So the ratios don't make sense. And the whole reason ratios don't make sense is because 0 is actually arbitrary. If 0 is arbitrary, then you're not in the ratio category. So it's the interval. And I believe that wraps us up for Chapter 1.1, just an introduction, terminology, some definitions that will carry through the rest of the book. So it's not my favorite part of the book, but it's an important part, and one that you really need to at least start getting a good grasp of as we head down into more formulaic and doing things with data. Okay, so hopefully I'll catch up with you in Chapter 1.2. Bye.